The mute button is so hard to find. But anyhow, welcome to Astronomy on Tap number 33, everybody. Thank you so much for being here. I am one of your MCs, MCM33.
And I'm MCMQG.
MCMQG. What does MQG stand for? I am M33 because that is a galaxy I study.
Well, I'm MQG because I study massive quiescent galaxies. MQGs.
Oh, I like it.
Yeah.
Right. Well, before we get to our wonderful speakers for the evening, we do have some announcements as per usual. Right? It is Black History Month, so we would like to take this opportunity to reaffirm our support for Black Lives Matter. You can find our full statement on the unofficial TAMU Astronomy website, which is tamu-astro.github.io.
And tonight we'll be having trivia as usual. So if you would like to participate, just go to tx.ag/AOT trivia. And tonight's trivia will be on the numerous contributions of African-American astronomers to the field. And so if you are slacking on your knowledge on that, that would be a good opportunity to just catch up on that. So again, the link will be tx.ag/AOT trivia.
Like and subscribe to stay notified about, I always forget this, but there is a standard YouTube plug. But anyhow, subscribe to our channel, like this video if you like what we do, and you will be notified anytime we've got a new event scheduled.
And we are on other social media platforms as well. So on Twitter and Instagram, we're at AoT_BCS. And on Facebook, we're at AoT BCS. Also, Astronomy on Tap doesn't just happen in Bryan College Station. It happens in several locations in the US and in many other locations in the world, including London, Chile, Taiwan, China, among others. So if you're interested in those events, you can check them out at astronomyontap.org/events.
Right. Our usual event when we are not in pandemic times is the Grand Stafford Theater in downtown Bryan. If you would like to support them, please Venmo any donations you can give to Jose-Quintana-20 and put Stafford Tip in the description of your payment.
Also, if you'd like to support the great work that we are doing here at AoT BCS, feel free to support us at Venmo or Cash App using this tag over here, AoT BCS. And if you donate $15, you will get an AoT-shirt. Unfortunately, none of us is wearing that now, but I can assure you it's a cool shirt because I bought it. So feel free to do that as well.
Our next event will be the third Wednesday of March, which is March 17th, same time, same virtual place.
Also, if you have any questions, we have a really fun-packed evening for you tonight and some amazing talk. So if you have any questions, feel free to put the questions in the live chat. We'll ask them at the end of the talk.
Right. And without further ado, it is time for our first speaker, who, fun fact, is technically from out of town. I think this is the first time we've done that. Or maybe not. I'm not sure, actually. Anyhow, please welcome Morgan Koenig. Oh, cool. Okay, and I do have a short bio. So, Morgan is a PhD candidate in theoretical cosmology at the University of California, Davis. Her work focuses on understanding how the universe started, as well as unraveling the nature of dark energy. Still, we don't know what it is yet, but thank you for working on it. When Morgan's not on campus, you can find her at the ballet studio under normal circumstances, of course. So without further ado, please take it away.
All right, hi everyone, and thank you for having me. And so today I'm going to talk to you a little bit about the beginning of the universe and something that I have been working on called inflation. So yeah, as mentioned earlier, I am a cosmologist, which means that I study the cosmos as a whole. And so I'm going to try to explain to you what is this inflation that we talk about in cosmology. But before we get started, let's look at cosmology. And cosmology is one of the oldest area that humans have been fascinated about. And we can already look at cavemen and the drawing that they had in their caves. And what they were representing was already their cosmology, because cosmology really means the understanding of your environment. So of course, here you would only see cattle and representation of nature, because that was their cosmology. So once again, the cosmology can date back to the Neolithic era, from 20,000 to 100,000 years before Christ. So of course, then when we talk about cosmology, we're mainly focusing on the stars and what we see in the cosmos. And here we can see a picture of the Nebraska disk, which is the earliest recorded astronomical observation. So at that point, humans started to expand their horizon and looking at the night sky as their environment. And this dates to 1600 years before Christ. And so if we look at earlier cosmologies, it was very different from, again, the cosmologies that we have today. So let's take an example with the Egyptian cosmology. And what we can notice is, first of all, it was always connected to their religion. Their understanding of space and the stars and the cosmos was connected to their religion. And here the earth is represented by this goddess that is laying, the goddess Geb, on top of which is the goddess of the air, Nut, and then the arch goddess is the goddess of the sky, Shu. And what is interesting in that representation of the cosmos is that it is a cosmos that has always been, that is eternal, that is not changing in time. And we can also see that in the Greek cosmology or the Hebrew cosmology, where again, we see the same thing. The earth is at the center, and on top of it is the firmament with a star. We have the heaven on top of it, and we have the deep, the underworld, the ground behind it. So of course, one common point between all those cosmologies, again, is that they're connected to a religion, they're connected to God, and there is always a creation history where God created the earth, the sky, and everything that we see. Those cosmology also present a universe that was created as is, and that is not changing over time, or at least there's something cyclical. It's not expanding, contracting, it just is as we can see it. Also, in all of those, the Earth has a very special place. It is at the center of the universe. It is unique, and it is where everything is connected to. And so there is going to be a big break, of course, between ancient cosmology and modern cosmology. So one of the biggest difference came when Galileo realized or expressed that the Earth is not at the center of the universe. So in 16th, 17th century, the Earth is going to lose its spatial position on in the sky, and it's just going to be one planet among a lot of other planets. But we still have an idea of a static universe, a universe that is not evolving in time. So this is what we know today about the cosmos. Of course, a lot is very different from the early cosmology, and it's very different from what Galileo knows. So what we know is something created, started the universe. Then it's going to be followed by this period of inflation that is going to be an accelerated expansion. We have to wait until 0.1 second to see the first little elementary particles. We have to wait until 3 minutes to see the first hydrogen atom. And between the beginning of the universe and 380,000 years, the universe is very dense, it's very opaque, meaning that we today cannot see through that. It's a universe that's very dense, where the photon, the light particle, do not reach us. Then after the cosmic microwave background at 380,000 years after the Big Bang, we have to wait millions of years before we can see the first stars. And this is what we call the dark ages, because the universe is very dark at that time. Now we know that the universe is 13.8 billion years old, and it's made out of galaxies and stars and clusters of galaxies and a lot of really complex structures. So now one question that we can ask is, it seems that the universe changed over time. It expanded, we had the right structure, we have galaxies, but how did it expand? Is it expanding and then contracting? Is it expanding at a constant rate? Is it expanding faster, slower, accelerated, etc., etc.? How is it expanding? How is it growing? How fast is it growing? And so how do we get our information in astronomy, astrophysics, cosmology? We get the information looking at light. The light that it is emitted by galaxies that are far away tell us information about how the universe was a long time ago. For example, if you look at the sun, you see the sun 8 minutes in the past, because it's going to take 8 minutes for the photon, the light particle, to reach your eye. So again, cosmologists look at galaxies far away to try to understand the dynamic of the universe, how the universe expanded. And the question they were trying to answer is it growing faster? Is it growing slower? Is it growing at the same rate? And so what they did is they looked at supernovae, which are stars that explode and that emit a lot of light. And by plotting them on graph, they realized they were able to show that the universe is expanding, so it's growing faster, and it's actually growing at an exponential rate. And that gave the Nobel Prize to Adam Rees, Schmidt, and Sol Perlmutter in 2011 for the discovery of the accelerated expansion of the universe. Okay, so now we want to get a little bit closer to the beginning of the universe. Okay, we know that now it's expanding at an accelerated rate, but again, we want to go a little closer to the beginning. So this map represents the oldest map of the universe that we have. This is a map of the universe at 380,000 years after the Big Bang. Now remember, the universe is 13.8 billion years old. So what we're looking at here is a very early primordial universe. At that time, we have hydrogen atoms, we have a little bit of helium, and that's it. And what we see here is a temperature fluctuation map. The red dots are hotter and the blue dots are colder. And this is the earliest map that we can have. We cannot see anything before that. So with this map, we need to try to get as much information as we can about the early universe. Okay, so again, the cosmic microwave background that I showed you is 300,000 years after the Big Bang. And what I'm going to talk, or what I'm studying, is inflation, which is right after the beginning. So how do we know anything about this time? So of course, inflation, again, it's the very beginning of the universe, and it has been studied extensively, looking at very complicated model, trying to find different scenarios, and it's a very active area of research. And that has been unraveled by those two physicists, Alan Guth and Andrea Albrecht. So again, what is inflation? What happened? The universe starts, and then it's going to expand extremely fast in a very short amount of time. So how short are we talking? So the inflation starts at 10 to the power negative 36 seconds and end at 10 to the power negative 32 seconds. So okay, what is this? So 10 to the negative 36 seconds is 0,350 second. And 10 to the negative 32 seconds is 0,310 second. So in that extremely short amount of time, the universe is not going to double in size. It's not going to be 10 times as big. It's not going to be 1,000,000 times as big. It's going to be 10 to the 26 bigger, meaning 10 or 1 followed by 26 0 bigger in that tiny amount of time. And that we know that the universe has to expand extremely fast in that very short period of time. So why do we need that? Because we needed to explain different parameters of the universe. One of them, and I'm not going to go into detail, is the fact that the universe is flat. We know it's flat, it's connected to the space-time of the universe, and inflation answers why it's flat. Another problem that we have is if we look at this cosmic microwave background, which tells us the difference of temperature, if you warm up your soup in the microwave, your soup is not going to be the same temperature everywhere. But the cosmic microwave background is basically the same temperature everywhere on a huge scale. So how come that the universe at that time was basically the same temperature? And again, thinking about a time, a small era of time with an incredible expansion explains why the universe is so homogeneous, why it's basically the same temperature everywhere. It also explains other problems, such as the monopole problem. This is connected to the fact that there are no magnetic monopole. For example, you can have a positive electric charge, you can have a negative electric charge, but when you have a magnet and you break it, you get two magnets. You're never going to be able to isolate a north pole for your magnet and the south pole of your magnet. It's pretty strange, right? Well, inflation answers why we do not see any monopoles in the universe. So once again, why do we need inflation? We need inflation because it answers a lot of problems that cosmologists had for a long time. Inflation is, again, this period of time, very, very brief period of time when the universe is going to expand extremely fast. So now, maybe you feel like I cheated you because I told you I'm going to talk to you about the origin of the universe, and I didn't. I talked to you about what happened at 0,350, 1 second after the universe, but I never actually told you what happened at t equals 0. So first of all, there are multiple models of the origin of the universe. Maybe there was a universe that was contracting, and then when it got small enough, it expanded again and gave us the universe that we have today. But what I want you to understand is that it's very difficult to talk about the beginning of the universe because we talk in terms of time t equals 0. But how do we define time when before that time, there was no time? And so again, what I want you to get from it is that in cosmology, we study the universe after it was created. But the question of the origin of the universe, of what was before, what started it, what happened exactly at the beginning, is not a physics question. It's a metaphysical question. It's a question that physics is not necessarily trying to answer, but maybe working with philosophers, working with artists, working all together, we can have a better comprehension of what is the origin of the universe. All right, thank you.
All right, thank you so much, Morgan. Inflation is always one of those things that I just can't wrap my head around it. So it was really cool to hear your explanation. I understood a lot more than I have before. Oh, well, we do have a question from the chat. And I guess you kind of answered this, but maybe if you wanted to go into the research aspect of it more. This question comes from Paulina Delgado. How do you guys know that things happened milliseconds after the Big Bang?
Milliseconds after the Big Bang? That's a very good question. And so this is something that people that study particle physics, for example, can modelize or can look at. What we know is we have an idea about the energy that were involved after the Big Bang, the energy level, and we are able to reproduce some of those energy level in the lab. For example, the CERN is doing that, looking at particles colliding and trying to simulate the beginning of the universe. And again, by knowing the temperature, knowing the energy that was involved, we're able to know what kind of particle were created at that time.
Thanks. This question also comes from the Delgado family, this time from Sylvie. Do you stay up at night thinking about the time before t equals 0 / how the universe started?
Yeah, I think I used to. But now I'm deciding to focus my energy on, I don't know, understanding dark energy that is pretty recent in our universe. So I'm going a little bit further away from the beginning of the universe. But yeah, but it's not something that I think, I mean, everybody thinks about it. I think it's just, you know, the question of the origin is, it's such a human question.
On that
Just
note,
to follow that up, can you tell us in just a few sentences what your research on dark energy is about?
Yes. So dark energy. So at some point, I explained how the universe is expanding at an accelerated rate today. And so one way to explain this accelerated expansion is we need a fuel, and the fuel is dark energy. So now the question is, what is the nature of dark energy? And there are two main schools for this. One of them is the cosmological constant. So without going into detail, you look at the Einstein's equation, you add a term and you say, this is my dark energy. But what I'm focusing on is trying to explain dark energy as a particle that behaves like dark energy. Now, one of the issues is if dark energy dominates at any point in time, it's going to keep dominating. But we know it's only dominating now. So the question is, where was this particle hiding, or how was it hiding before? And how come that it started behaving like dark energy just recently in terms of the history of the cosmos? If that makes sense.
Yeah, it makes sense. That's very fascinating. So this is, I guess, a contentious question, but what do you think is the most likely candidate for a dark energy particle?
I mean, I'm really biased because it's mainly based on my advisor, but I think the axion, I don't know if you heard about this, is probably a good candidate. But if you talk to physicists that have been in the business long ago, some of them tell you it's neither of those. It's not a cosmological constant. It's not a particle. It's maybe something else that we haven't even thought about yet. Mm-hmm.
that's really cool. Question for me. Of the ancient cosmologies that you talked about at the start of your talk, do you have a favorite among them, or do you like all of them? Because myths are cool.
I mean, I have an obvious favorite. I mean, the Egyptian one, because, you know, Egyptians were black, so those were my people. Yeah.
Very fair. Yeah, well, I guess we can give you a few more minutes if people have questions. We don't have any more questions in the chat, but we do have a lot of high fives and applause. So thank you for a great talk.
All right. Well, thank you for inviting me again. And yeah, I hope that that you got curious about the beginning of the universe and trying to understand what happens as early as possible. The stars are cool. The galaxies are amazing. But looking at, very dense universe is also very interesting, in my opinion. So again, thank you for having me, and yeah, bye.
Thank you so much, Morgan. That was a very fascinating talk. So now we're going to have MC Carbon Queen tell us about who's up, not what's up. So she's going to be sharing with us some of the work that's going on with the Black and X community. And so we'll go ahead and hand it over to MC Carbon Queen.
Hello. All right, let me share my screen. On a computer that will delay for 3 seconds to make me hurt. There we go. Okay. So welcome. Let's talk about, normally this segment would be called What's Up, but we're going to start calling it Who's Up. And we're gonna make that work now. Okay, and there might be a delay on my slides, Linux, haha. All right, so just to kind of describe what this is. So Who's Up is gonna be kind of a semi-recurring segment starting this month. And we're gonna be highlighting different active astronomers and the awesome science and work that they do. And so for every person I mention, I'm going to include all their social media information so you can go and follow them on social media. So for this month, what we're gonna do is I'm going to talk about, this is gonna be the only time I'm gonna talk about more than just astronomers. I'm also gonna talk about a few other scientists. And there's a reason, partly because it is Black History Month. I wanna focus on this really awesome movement that started. So in the past year, a lot of groups have formed on Twitter and other social media platforms that kind of go by the name of Black in X. So Black in Data, Black in Neuro, Black in Physics, Black in Marine Science, Black in Genetics, and Black in Astro. So this is just a handful of the ones that exist. They're amazing, awesome platforms. The purpose of these was kind of to create a community of Black scientists in these different subfields so that, one, they can actually connect with each other, they can uplift each other and their science, and it's a lot easier to find people and, you know, promote other things. And so it's just really cool. These are really cool programs you can, and different platforms you can look at. And so, of course, the one we'll mostly focus on is the Black and Astro one. But before we really dive into what these different Black and X groups are doing this month, I wanted to first highlight a particular person. So this is Ashley Walker. She's an astrochemist, a planetary scientist, a science communicator, and activist, and just like an amazing person all around. She's just super cool. So you can find her on Twitter, and there's her Venmo, which I'll get to in a second. But so in March, or not March, in February of 2019, so during Black History Month, she did this Twitter series where she was essentially just highlighting, I think, nearly every single Black astronomer that was actively doing science at the time, including our very own NCMQG. And it was really cool. It was this awesome series. And so it's since been collaborated and combined into this list called Black Astronomers You Should Know. Feel free to check out that list. I think they're continually updating it. And so throughout the years, Ashley herself has continued to add more things to it. And then recently, because of all these Black and X groups forming, she founded the Black and Astro group and is now co-organizer of it. She also helped found and co-organize the Black and Physics group and the Black and Chem group as well. So she's just kind of doing everything. So additionally, on top of that, Ashley and a few others partnered with this group called Astrobytes. And for those who are unfamiliar, Astrobytes is this really cool resource that MCM33 is actually a part of. And it's essentially this online astrophysical journal where they summarize in easier words, different papers that come out in astronomy. And then they also talk about different social issues and also highlight different things that will affect grad students, like how to cope through grad school and things like that. So it's a really cool resource. And so at one point they had a whole week that was just hashtag Black and Astro Week. And they interviewed different Black astronomers. They also had different opinion pieces written. It was really cool. And so I'm highlighting here a screenshot from their Twitter account where they had the interview with Ashley Walker herself. You should definitely go check these out. Also, it was just pointed out, Ashley just got a Wikipedia page. And so it's, yeah, super exciting for her. So the reason why I've included her Venmo is partly because, you know, Ashley does so much just constantly. She's always doing something, always uplifting other people, trying to make sure that everyone gets known. And a lot of the work that she does is entirely unpaid. And so if you are able to, or you have the means to, and you're willing to support her, please just send her money. She so deserves it. Everyone just share the love with her because she absolutely deserves this. So now to move on, now we're going to talk about Black and Astro in particular. So I'm only going to highlight 2 Black and X ones because I have limited time here with y'all. But I'll leave this as an educational resource for the user to go look up all the others and follow them and learn all about the awesome scientists that they talk about. So first, we're going to talk about Black and Astro. So Black and Astro, this month, what they've been doing is they've just been highlighting various Black astronomers, kind of like what Ashley did throughout the month. And so here's just some of the screenshots I took of just the different people that they're highlighting. And they're also occasionally doing a throwback to the list that Ashley had made in 2019 with some updates. They also have an Instagram page where they're doing more features of different people. And then they also are using this platform to, you know, retweet other accounts that are doing things like the American Astronomical Society, which is kind of like the big United States Society for Astronomy, professional society. They're also doing Black History Month highlights. And so they're retweeting those. They're also retweeting a lot of other things, including just random stuff that the scientists are saying. So it's just a really cool site. And so you should definitely check out this platform. The other group I wanted to talk about is the Black and Neuro group. And so the Black and Neuro is for all these neuroscientists, and they've actually been incredibly active. They're doing nearly daily posts. They're highlighting past and present Black neuroscientists. And it's just been super cool to learn about all these different neuroscientists. And really cool whenever they are retweeting it themselves. And so Black and Neuro has also been really active in creating some workshops and seminars and stuff. And so you should absolutely go follow them and keep up on all those things and share it with anyone you think who would be interested. And, you know, just kind of signal boost all this stuff. So like I said, I'm going to leave all the other Black and X groups for you to go look at because of my limited time. And just go see what they're doing, you know, keep tabs and support and uplift and signal boost. They're super cool. And so, yeah, so that's who's up this month. Stay tuned. We'll be doing more scientist highlights through other AoT events. And I'll just kind of be going crazy and having fun with it. So thank you so much. That is it. That's who's up.
Thank you so much, Carbon Queen. That was really cool. And yeah, actually, she literally got the Wikipedia page today, which is
so exciting.
Yeah. All right. Well, next up, we have Dark Matter Dude with In the News.
Hello.
Dude.
I'm gonna try to share my screen now. Hopefully this works. Okay, what's up, everybody? We are going to be talking about what happened in the news this month. This is the month of February. So yeah, let's just kind of get started. One big thing that happened that probably everyone has heard of, and if you haven't, now you will, is that Perseverance, which is a new Mars rover that NASA launched a few months ago, has landed on Mars. And this caused a huge media storm. There were a whole bunch of stories, really awesome images. I'm not going to talk about this because I made these slides for last week, and Perseverance landed after I made these slides. So we're just going to shove this to next month, but you'll hear all about it. I'll collate everything together. We'll have a party. But don't hate on me in the comments. We're just gonna move past Perseverance now. So yeah, there's a really cool result looking at basically trying to detect an exoplanet around our nearest star. So Alpha Centauri. So Alpha Centauri is a triple star system. Possibly, and so what we're trying to find here, what these people were trying to find was a planet around Alpha Cen A. So that's two stars that are in binary, and then there's a third star that's kind of orbiting around it. And so if you zoom in on one of those two stars that's in the binary, we're trying to find a planet there. This is really hard to do. But you can basically directly image the planet. So you're not using anything like a transit where you look at if a planet goes in front of a star and that blocks some of the light. We're not doing any of that business. We're directly taking an image of what we think is the planet. We're using infrared because it's easier to do at those wavelengths. And the specific wavelength or energy that they were looking at was very well tuned to find cool planets. So those are ones that are probably further away from their star. And so they actually found something that might be a planet. So we're looking at if we zoom in on this frame here, this little blob right here, that's the planet we're talking about. And so there's lots of image processing that goes into this. There's all kinds of artifacts. You've got these long streaks here, these kind of circular patterns here. So there's lots of image processing that's going on, and this might be affected by, this might be an image artifact, but we're the people who wrote this article are pretty sure that it's not. They also used a coronagraph and that is basically just something that they put directly on the telescope to block the light coming from the star. Simple enough. And so this is really like it's important to think that this might not be a planet. It might be just like a cloud of dust happens. So one of the really important things is to wait. We really want to get more data. What would really probably be really convincing is if we wait a couple of months to years and take basically repeat this process, and the dust cloud moves over on the other side as if it's completing an orbit, that would be pretty convincing that this is a real planet. So keep this in your back pocket, but Alpha Centauri might have a planet, which is super cool. Black hole swarm. Okay, so this is really exciting. So we're looking for what's called an intermediate mass black hole. So what that basically means is there's lots of black holes that are like a few to tens of the mass of the sun. And then there's supermassive black holes that are always at the centers of big galaxies. And those are like millions of times the mass of the sun. So we're looking there's a gap there. And a lot of astronomers think that there should be black holes that are in that gap. And one of the best ways to find those are globular clusters. So this is one globular cluster, NGC 6937. I looked this up right beforehand and didn't add it to my notes, so we're gonna go with that. So using data from the Hubble Space Telescope, Gaia, which we've talked about here, the Very Large Telescope, which is, you know, astronomers demonstrating how good they are naming things again. And so the idea here is that if you look at the motions of stars very close to the cluster, you can kind of tease out what the mass is of that cluster and the mass profile. And you can check and see if that mass is, you know, more than you'd expect just from counting up all the mass in the starlight. And the idea is that maybe there's an intermediate mass black hole there. So they tried looking for that, and what they actually found, it wasn't the signature of one black hole, but the idea was that you had about 1,000 to 2,000 total solar masses of, you know, not light emitting matter, so something like a black hole, spread out over half a light year. And so basically that is a swarm of smaller black holes that are just kind of spread out and around this, is the idea. So that's fascinating. Part of the way that they're kind of ruling out that it's an intermediate mass black hole is if you look at all the stellar motions and all the measurements, you can still get an intermediate mass black hole that works. But basically, if another black hole a smaller black hole came in, this bigger black hole that would be in the center would have gotten kicked out of the globular cluster during a merger. So basically, probably not an intermediate black hole. Sorry, but we get swarms of black holes instead, which I think is like super cool. Okay, we're back. So I think I've talked about this before, but there have been a lot of news stories lately about Oumuamua, which is sort of a new visitor to our solar system. So back in 2017, we got a not comet, but like a chunk of rock, basically, entered our solar system, came from somewhere else. This was the first time that we had detected this type of thing happening. It was on a super eccentric orbit. You might be able to see the image here. So it came in on this orbit and then spiked out. And it's a super eccentric, very interesting. There were two weird things about Oumuamua, besides the fact that it was the first time that we found something outside of our solar system coming back in. So the two weird things, its brightness changed in a pretty consistent way and by a pretty large amount, something like 15 times. And so the way that astronomers have kind of figured out how to explain that is basically it has a weird shape. It's kind of like a cigar shape. You can see that kind of flattened pancakey image there. And it's tumbling relative to the sun and our perspective. And so what that means is that as it's rotating and tumbling, more of the sun's light gets reflected back at us. And so that makes it appear brighter. Cool, great. And then there was this weird thing where it seemed to get like a kick going out, like a sudden acceleration as it was leaving the immediate vicinity of the sun. There's lots of kind of normal ways this can happen. You can have uneven heating due to that tumbling effect that we talked about earlier, and that we've observed uneven heating in tumbling objects causing weird accelerations before. Like that's a perfectly explainable thing. We see it with rockets a lot. So that could happen. Also, there could have been just like a cloud of basically like a jet of gas that it kind of burped and lost mass and shot faster a little bit after that. So there's weird things about Oumuamua, but basically we have ideas of what's going on. Okay. So now why this was in the news, and we're going to have to talk about that Harvard dude, that Harvard astronomer. And you're going to get a rant here. An astronomer at Harvard named Avi Loeb, the department head at Harvard, has basically convinced himself that Oumuamua, this extrasolar object is aliens. Like it's just an alien spaceship. And so he's been very insistent about this for the past couple of years, and wrote a book saying, hey, we've been visited by aliens, and the rest of the astronomy community is wrong about the fact that this wasn't aliens. And he is a sole truth teller. I'm even gonna like stop sharing my screen because there's not a whole lot more to talk about. Well, okay, whatever, I'll come back to it. And so, right, so there's a lot of things that I have to say about this. I'm gonna try to keep it to 3. So the main one is that like how scientific consensus is built. So it's not, hey, I have you know somebody comes up with an idea, and then you propose a theory and you come up with a way to test it, and then you go ahead and test that thing. And there's an idea that big extraordinary claims require extraordinary evidence, and we just don't have that evidence for Oumuamua. The broad like 99% of the scientific community is basically like, yeah, this is an alien. Like there's reason, like normal ways to explain this. Weird, but normal. And Avi is basically just saying, no, it's aliens, you're wrong, and telling the media this. And there's kind of this important idea that how stories are presented in the media and how things are adjudicated in the media is different from science. So on science, you make incremental changes, you kind of have a collaborative fashion, you grow off of each other and test each other's ideas, and eventually whatever's right will come on top. In the media, this doesn't really happen, right? If you have an argument, you want one side argue, you give one person arguing one thing and another person arguing the other. And so that implies that both are equal. And that's just not how art, like figuring things out in science works, but it's how it's kind of turning out in the media. I wrote down my points so that I wouldn't get too ranty and rambly here. Another thing that's really important is that we attach a lot of prestige to elitism here. So because this dude is at Harvard, we have like a lot, like there's this idea that, oh, he's at Harvard, he must be right. And to take his word over some smaller institution that you might not have heard of, who may even be an expert in the field, but it's very easy for anybody, and especially the media, to just go, oh, Harvard astronomer says that we've been visited by aliens before. And the Harvard bit links it to, oh, this is true. And that's not it either. And so then there's a third aspect. And so kind of a little bit of background on this. Avi Loeb went on a kind of scientific panel broadcast, live feed to YouTube talking about Oumuamua and just the concept that he describes in his book. And a lot of experts in kind of the extrasolar community and people who work on aliens were like finding aliens and detecting aliens were also there. And one of those experts, Joel Tarter, who's a titan in this field, basically offered kind of her view on, hey, Avi, we have a lot of people working on this alien problem. Maybe you should work with us and not do what you're doing to sell books. And he basically kind of shouted her down. And I don't want to get too far into that, but I just like, one thing that our society also does is reward people who speak the loudest and speak the most aggressively. And so whenever there's somebody who is speaking loudly, speaking aggressively, is using the label of some elite credential, and is selling you a book, I would be more skeptical of that than otherwise. So that's my rant. And then to kind of bring this back into some happy news, I'm going to click over here because I lost it. So this is just kind of, and I like to close these with a really cool image that has sort of surfaced on social media and whatnot. So this was, making the rounds on social media recently. This is super cool. So this is an image of the sun taken by very fast, very low mass particles called neutrinos through the Earth. And so what's happening here is because neutrinos are super light, they don't interact with anything really. It's a very low probability that it'll scatter off like a molecule or something like that. So because this doesn't happen very often, neutrinos can just burrow through the Earth. So the sun produces neutrinos. Those neutrinos just kind of burrow through the Earth and like will just travel straight through it. You're being bombarded with neutrinos, a lot of them every second. And so you can build a neutrino detector. People, physicists have done this, and build giant detectors. And one of those biggest signals that you get is the sun. And so this is the sun in neutrinos after they've tunneled through the Earth and hit the detector. Which I just think is like, this is super, super cool. This isn't actually the real physical size of the sun. This is like large, this is the equivalent of a large swath of the sky, which is another fascinating thing. So yeah, that's what was in the news.
Thank you so much, Dark Matter Dude. For full disclosure, there was hating in the chat over Perseverance's mission, and possibly a pepper shaker that I think was supposed to be salt, so people are also salty.
Okay, well, they'll get over it. I promise. In 3 weeks, I'm gonna do all the hype you want on Perseverance and Mars. I promise.
There's been so much over the past, I don't know, week? Less than a week. I don't know.
Yeah.
I'm excited.
Well, thank you, Dark Matter Dude. Just as a reminder, if you haven't done the trivia yet, this is your last chance to do so. So just go to tx.ag/AOT trivia for a chance to win some really cool digital prizes since we're in COVID. So our next segment is going to be We Got Published, and we'll have Carbon Queen returning to do that for us.
There we go. Sorry, it takes a second. Hi. Okay, I'm back. So we've done this segment a few times before, I think. Generally, it's whenever we have a paper that gets published in like a prestigious astrophysical journal. This is a paper that I wrote last year, a manuscript. This actually was not published in an astrophysical journal, but it was published in this engineering society's conference proceedings, which for engineering people is considered, they consider it like a professional paper. And so it still counts. So this was work I did as a visiting scholar at an observatory in Hawaii, where we were working on improving the precision of a world-class spectrograph. And so I'm just going to briefly talk about a few of the things about it, because I only have 5 minutes. So first I want to highlight the telescope. So this is the Keck telescope, or the Keck telescopes. There are 2 of them. I'm highlighting the one that I use, which is Keck 1. It was built first. The telescopes are located at the top of Mauna Kea, which is on the Big Island in Hawaii, and the elevation of over 13,000 feet. It's a 10-meter telescope, both of them are, and so 10-meter diameter, 30 feet diameter approximately, or as I tell children, it's 2 giraffes standing on top of each other. Over here on the right is just showing you a map of Hawaii and the location of the Keck Observatory headquarters. Because these telescopes on the Mauna are so high up, the headquarters are never there. The headquarters are down in like towns, the base of the mountain, and you essentially kind of remote. And there are people up there who drive the telescope for you. So it's really cool. Very prestigious telescopes, incredibly hard to get telescope time on them. And so the telescope houses a lot of different instruments, but the particular instrument I'm focusing on is this spectrograph called MOSFIRE, which is love of my life. So this spectrograph is amazing. It's a near-infrared spectrograph. So for anyone unfamiliar, near-infrared, just think of it like heat vision or thermal vision. That's just what infrared would be. So these are larger wavelengths, They look at redder, quote unquote, light, you know, and so it's kind of actually hard to see near infrared light through the atmosphere because the atmosphere is not our friend in the near infrared. So this spectrograph is incredibly sensitive. It can look at lots of galaxies at once, like it's super cool. And for people who would find these numbers useful, it has a pretty high resolution, relatively speaking, of about 3,300 for R. And then the wavelength coverage is about 1 to 2.4 microns. And so what you're seeing on the left-hand side is just a picture of the spectrograph. It is actually huge. I cropped the person out, but that is an arm and there's an elbow, just to give you an idea of size. It's a pretty big thing, and it has to be, right, if it's put on this massive telescope. Over here is the light path. This is essentially what engineers would look at, and astronomers who also build instruments would look at to understand exactly how the light bounces inside of this thing to get us the beautiful data that we need. So you don't really need to care too much about that. So the science that this particular spectrograph has enabled is wide-reaching and amazing. So it's looked at, you know, brown dwarf stars. It's looked at dead, you know, quote-unquote galaxies, also called quiescent galaxies. It's looked at exoplanets. It's looked at populations of stars. It's looked at planets in our own solar system. It's looked at some of the first galaxies ever discovered, and I made that the largest text because that's my science and that's what I care about. It's also looked at so much more that I haven't included here. It's an amazing spectrograph, an amazing instrument, and everyone wants to use it. It's so hard to get time on this telescope. So mostly I want to focus on, okay, I'm talking about telescopes, and we've had some talks before that are kind of describe how this even works. How do you get data from a telescope? But just to kind of briefly remind you, this is a schematic from my paper showing just a cartoon I made where you have this, you know, the 10-meter wide telescope, which is actually a combination of little tiny mirror segments put together. So on the left-hand side, you have light incoming. It bounces off the primary mirror, bounces up to the secondary mirror, which is this gray box. And then it bounces down to the center of the primary mirror where there's a hole, and then the instrument is behind it. And so the instrument is located here. It's little blue blocks, which is hilariously looks kind of just like Mossfire. This is what we call the Cassegrain focus instrument. And so this is located at the very back of the telescope. This is where Mossfire would be located when they use Mossfire. And the important thing about this is, as the telescope moves around throughout the night, there is gravity pulling on everything, right? That's just how life is when you live on a planet. And so gravity is pulling on the instrument at the back of the telescope differently as the telescope is changing. So like as the telescope looks one way, gravity is pulling on the instrument a certain way. As it moves, it's pulling on a different way. And so it's actually really important to characterize how gravity is affecting the instrument, because that will affect all the data you get from it. So to kind of describe this then, what the problem was is usually, you know, you're very careful when you design these instruments, and you very carefully compensate for how gravity is affecting everything. Now the problem is when you look at a particular galaxy for many hours using the spectrograph, which not many people do. My science is one of the few that requires this. We noticed that this precision isn't actually as good as it could be. Like there's a little bit of what we call a drift. And so all I really want you to focus on is, whenever it pops up for you, this blue box is an acceptable threshold. So these squiggly lines, if they're within the blue box, it doesn't matter. It's doing its job. It's doing fine. But once these squiggly lines come outside of the blue box, based on this information, this is telling us that the telescope and the model that's trying to correct for how gravity is pulling an instrument isn't doing as good of a job as it could for these very, very long observations that we're doing. And so that's important because we need every single photon of light we can get for these really faint galaxies we're looking at. And so this is where we come in. And so this is when I went to go live at Keck Observatory for 2 months and work there as a visiting scholar. We tested different parts of the instrument to see what was causing this drift. To spare you all the details, I'm not going to go into more detail. I will leave that as a, you go read if you want, check out our paper. I put a too long didn't read here. So we're pretty sure that we found the culprit from all the things that we tested, and we're conducting more testing. We'll be conducting more testing to improve the model that was used, and therefore improve the precision of this world-class spectrograph. So that will be in the near future. And I mostly just wanted to highlight like this. I liked writing this paper because I had so much fun making all of these plots, and these are just a few of them. I just kind of went crazy. This was my chance to do whatever I wanted with plots, and no one could tell me no. And so if you even just look at the paper to enjoy my plots, that would be great. But yeah, we got published. So thank you very much.
Thank you for sharing, Carbon Queen, and congratulations again.
Thanks.
All right, so I hope you've done your trivia because now we're going to go over the answers. So drum roll. Okay. Showing on Tap trivia. Question 1. Since 1995, the fraction of bachelor's degrees in astronomy awarded to African American students has A, increased and is not proportional to the population, B, increased but is still not proportional to the population, C, decreased but is proportional to the population, D, stayed about the same and is not proportional to the population. And the answer is D, it stayed about the same and is still not proportional to the population, which still tells us that we have a long way to go. And this graph here just illustrates that problem. So you can see, I'm not sure if this Google Slides thing here is blocking the legend at the bottom, but you can see what this trend is like for the different fields. So physics, chemistry, earth sciences, and astronomy in the green, and it has stayed relatively flat since 1995. So question 2, Dwight, the first Black astronaut trainee, was forced to resign due to racial discrimination. He then became D, all of the above. So a jack of all trades, if you will. And this is just a video here of Ed Dwight that we're going to show. All right. So for question 3, Arnaldo Tamayo Mendez, I hope I didn't butcher that name, the first person of African descent to go to space flew in which space program? And the answer is B, the Soviet Union Soyuz program. And for question 4, in what year did Dr. Mae Jemison become the first Black woman to go to space? And the answer is in 1992. So we'll go ahead and play this video as well on Dr. Mae Jemison.
Area has never been enough. Sure, we know her as the first African-American woman in space, but there's so much more that makes Jemison extraordinary. Mae grew up in Chicago, where like most kids, she dreamed of being a fashion designer, archaeologist, or astronaut. She decided at an early age, she would go to space. Astronauts back then were exclusively white and male, but those aboard the USS Enterprise on Star Trek were different, particularly Lieutenant Uhura. And that allowed young Mae to see someone that looked like her in space. Even as a kid, she was extraordinary. She graduated high school at 16 and went to Stanford. She double majored in chemical engineering and African and Afro-American studies. During her junior year, she had to decide if she should be a doctor or a professional dancer, which were both legitimate options for her. She chose medical school and even worked in a Cambodian refugee camp in Thailand. And she didn't just become a doctor. In 1983, she became the Area Peace Corps Medical Officer for Sierra Leone and Liberia in West Africa. She managed all the healthcare for the Peace Corps, wrote manuals for self-care, researched rabies with the CDC, and was in charge of medical care for the US Embassy. And she was 27. After 2 years there, she returned to America and began working as a general practitioner in Los Angeles and took graduate-level engineering classes at the same time. And even then, she was still like, I could do more. So she applied to become an astronaut in 1985 and wasn't deterred when the Challenger exploded the next year. She reapplied and was selected out of 2,000 applicants to train to be an astronaut.
And liftoff of Space Shuttle Endeavour.
September 12th, 1992, Jemison made history when she took off aboard the Endeavour for 8 days in space. As a science mission specialist, her job was to conduct experiments on the crew on motion sickness and bone cells. After her big dream was realized, Jemison decided to take it easy as an environmental studies professor at Dartmouth College, starting an educational nonprofit, a science camp, and serving as principal for 100 Year Starship, an initiative working to travel beyond our solar system in the next 100 years. Oh, and in 1993, she guest starred on Star Trek: The Next Generation. Jemison has gone back and forth on this whole role model thing. She didn't really want to be the poster child for Black female astronauts, but she did want young girls, and the old white men that would hire them someday, to see that your race or gender doesn't limit you.
Now for question 5. Oops. Dr. Barbara A. Williams, the first African-American woman to get a PhD in astronomy, completed her PhD in, the answer is B, 1981. Question 6, Dr. George Carruthers invented the first moon-based observatory, the far ultraviolet camera or spectrograph used during, the answer is A, the Apollo 16 mission. For question 7, Katherine Johnson worked as a computer for NASA. Her calculations were essential to all of the below missions except, the answer is D, trick question. Her work was essential in all of the above. So no wonder her work in recent years has gotten so much coverage in books and in movies like Hidden Figures, etc., etc. And this is a short video on Katherine Johnson that will show.
celestial body for the first time in history, overcame terrestrial gravity and flew into space.
Question 8. As of January 2021, how many African-American women have been awarded PhDs in astronomy? The answer is just 22, so pretty grim number. Question 9. Dr. Harvey Washington Banks, the first African-American scientist to earn a PhD in astronomy, specialized in A, studying spectroscopy and the shape of the Earth. And this is a short video on Dr. Harvey.
Jumping forward to the 20th century, we have Harvey Washington Banks. He was the first African-American to earn a doctorate in astronomy, which he did in 1961 from Georgetown University. His dissertation was titled The First Spectrum of Titanium from 6,000 to 3,000 angstroms. Real exciting stuff. Well, for astronomers. His research focused on celestial mechanics, geodetic measurements, as well as spectroscopy. But the focus of his academic career after receiving his doctorate was really teaching. And he was a professor at Delaware State College and Howard University for many years.
All right. Question 10, which I believe is our last question. Dr. Jerita Holbrook is known for studying indigenous African astronomy, but first she got a PhD studying star formation. So a well-rounded astronomer she is. And that is all for trivia. I hope you're able to get as many questions as possible, right?
Me, Jemison did so much.
It's really remarkable just listening to their stories and just seeing all the wonderful things that they accomplished.
Yeah. Well, before we leave you all and let you go from Astronomy on Tap number 33, we're going to loop through our announcements again. So, I wish I knew the Jeopardy theme better. It's very good for interstitial clients. But yes, first off, it was Black History Month, which we hope we highlighted in the trivia. And you can definitely go back and watch this stream after it's been posted to refresh yourself on all the amazing work that the Black scientists highlighted in that presentation did and are doing. You can also go to our website, tamu-astro.github.io, to see our statements in support of Black Lives Matter. Mr. Johns, next month, maybe.
Apologies. Again, we hope you're able to participate in the trivia. If you did, you'll get an email from us if you won. So look out for that.
Like and subscribe if you would like to get updates from this channel. For instance, when we have our next event scheduled, and also something algorithm, something.
And please follow us on other social media accounts, so Twitter, Instagram, Facebook. If you want us to, we'll create a TikTok, whatever you want us to do, just stay in touch. And you can also check out the other Astronomy on Tap events at this link here.
Also, to harken back to the YouTube very briefly before this, we are 4 subscribers away from 100. So if everyone on this watching this video right now could tell 4 of their friends, there's a chance we'll get to 100. I'm saying that so we maximize our chances of getting to 100. But anyhow, in the before times, we have had this event at the Grand Stafford Theater in downtown Bryan. If you would like to support them, you can Venmo at Jose-Quintana-20 with Stafford Tip in the description. It will be much appreciated.
And you can also support Astronomy on Tap BCS by either Venmoing us or using Cash App, using this tag here. And again, you will get a shirt. It's a very cool shirt. It's lavender if you like bright colors or pretty colors, I suppose. So please feel free to do that if you are so inclined.
Our next event will be the next Thursday. Third Wednesday becomes Thursday. Third Wednesday of March, which is the 17th. Please do join us. It will be a lot of fun, as it always is.
Well, that is all that we have for you. We hope that you enjoyed the talk. We hope that you enjoyed everything that we had to share with you tonight. And we will see you at the next event.
Good night, everybody.